Welcome back, folks. Mr. Johnson with you once again. This is lecture 26. We're in section 6.6 of our textbook. We're on page 379 here, and this is a lecture about the polarity of molecules, how it is we determine whether or not a molecule is polar. Why we're doing that is that if we are able to determine whether or not a molecule is polar, we are then able to determine what type of intermolecular force it experiences with other like molecules and how strong those intermolecular forces might be. And that's part of that storyline that I shared with you at the start of lecture 20. And it's built on an understanding of predicting the shapes or structures of molecules. It's based on predicting the polarity of molecules, being able to use your understanding of VSEPR to know what the shapes of these molecules are. So I thought we'd start with a quick review from the last lecture you watched by Tyler DeWitt about shapes of molecules. So I've got a formula up here. It's beryllium dichloride. I've got the Lewis structure of beryllium dichloride written there. I want to remind you that beryllium is one of very few elements that will be satisfied with just 4 valence electrons. It has what's called an incomplete octet, and even though beryllium is a metal, it can form covalent bonds. So this is beryllium dichloride. What we see is that beryllium has just 2 bonds coming off of it. It has just 2 things, as Tyler DeWitt referred to them as. I'm going to be calling them bonding pairs. Off of beryllium, off the central atom of beryllium, are 2 bonding pairs or bonding groups. 2 bonding electron groups. Again, Tyler DeWitt called them things. Well, when 2 electron groups want to get as far away from each other as possible, they do so in a linear fashion. So this is a linear molecule that we're looking at here. Where the electron groups get as far away from each other as possible by forming a line. So here is the 3D shape of beryllium dichloride, and again, it's linear. If you recollect from that VSEPR lecture, if the bonding group is a double bond, it acts the same way that does a single bond. It also wants to get away from the other electron group as best it can, and it does so by being linear. If this were a triple bond, it would also act like a double or a single bond and get as far away from the other electron group as possible, and it would be linear. So when there's just 2 things or electron groups or bonding groups coming off a central atom, we know the shape is linear. Here's another example. This is boron trihydride, BH3, and its Lewis structure is depicted beneath it. Boron is connected to the hydrogens through 3 single bonds. Boron can also have an incomplete octet. In fact, it will only have an incomplete octet. And it will only form 3 single bonds. When 3 things, or I'm going to be calling them electron groups, spread out evenly in space, they do so by forming a trigonal planar molecule. A trigonal planar molecule. And here is an example of a trigonal planar molecule where 3 electron groups are spreading out evenly in a trigonal planar shape. If one of these electron groups was a double bond, it would act like a single bond and would also spread itself out evenly, and it would be trigonal planar as well. So if 3 electron groups are spreading out evenly in space, 3 single bonds, 2 single bonds, and a double bond, we get a trigonal planar shape. Another example, here's the nitrite ion. It's NO2 1-. Here's the Lewis structure, which you would be able to draw on your own, where there's a single bond between the nitrogen and 1 oxygen and a double bond to the other one, and then there's this lone pair up top. There's this lone pair. Well, this is also 3 things, or 3 electron groups, coming off the central atom. One of those electron groups is a single bond, a bonding group. The other one is a double bond, a bonding group. And then this is a lone pair. But there's 3 electron groups coming off of them. 2 are bonding groups, and 1 is a lone pair or a non-bonding group. Got to realize that that non-bonding group, or that lone pair, acts kind of like a bond in that it has a similar shape, similar electron cloud shape, and repels just like the bonding groups fairly evenly, fairly equally. So when we have 3 electron groups coming off a central atom, but one of them is a lone pair, one of them is not a bonding group, then when we think about the shape, we have to think of the 3 electron groups spreading out evenly in space, but if one of those electron groups is a lone pair, this now stickle by itself is thought of as a lone pair, we're left with a molecule that is bent or V-shaped. When we talk about the shape of the molecule, we just talk about the shape that the atoms make and not the lone pair. So again, if there's 3 electron groups, they spread out in a trigonal planar shape. But if one of those electron groups is a lone pair, you're left with a molecule that's bent or V-shaped. Here are with methane, CH4, there is its Lewis structure. Carbon is bonded singly to 4 different hydrogens. There are 4 electron groups coming off this central carbon atom. They're all bonding groups. So if we contemplate the shape that these 4 electron groups, when they spread out evenly in space, will make, it, as you may recollect, gives us a tetrahedron. And remember, the angles in a tetrahedron are all 109.5 degrees. So there's a tetrahedron. But if one of those electron groups is a lone pair, there's 3 bonding groups and 1 electron group is a lone pair, then you are left with a molecule that is called trigonal pyramidal, or a trigonal pyramid. If there are 4 electron groups coming off the central atom, and 2 of them are lone pairs, and therefore only 2 of them are bonding groups, we are left with a molecule that is also bent or V-shaped, except these angles are less than they were in the trigonal planar bent V-shaped molecule from earlier. I want to remind everybody that trigonal planar molecules have 120 degree bond angles, but if there's a lone pair in a trigonal planar molecule, and you're left with a bent molecule, in fact, the angles are a little bit less than 120. And that's true of a tetrahedron, which has 109.5 degree bond angles, but if there's 1 or more lone pairs, those angles get shrunk a little bit because the lone pairs exert a little bit more repulsion than the bonding groups do, and you get angles in the bent molecule from a tetrahedron, or in the trigonal planar molecule in a tetrahedron, a little bit less than 109.5. So that was the quick review of Vesper. Partly why I did that is so that we can apply our understanding of the shapes of molecules to symmetry. The goal of this lecture is for you to be able to predict whether or not a molecule is overall polar. And for a molecule to be polar, and you'll hear me repeat this multiple times, for a molecule to be polar, the bonds in the molecule need to be polar, which I'll talk about in a moment, and the molecule needs to be asymmetrical. Again, for a molecule to overall be polar, the bonds need to be polar. We'll talk about what that means and why. And the molecule needs to be asymmetrical. So I first want to talk with you about how we can predict whether or not molecules are asymmetrical or not. I'm going to start with this linear molecule. Linear molecules are symmetrical, right? We can imagine a plane going right down the middle, and the left side of the plane and the right side of the plane are the same. Above the plane, below the plane are the same. Linear molecules are symmetrical as long as both peripheral atoms are the same. Linear molecules, once again, are symmetrical if both of the peripheral atoms are the same. But if one of the peripheral atoms is different than the other, it's no longer symmetrical. Again, linear molecules will be symmetrical if both peripheral atoms are the same, and they won't be symmetrical if both peripheral atoms are not the same. All right, let's go to a trigonal pyramidal molecule. Excuse me, I meant to say trigonal planar. Trigonal planar molecules are also symmetrical. There's multiple axes along which they're symmetrical, as long as the peripheral atoms are the same. This is a symmetrical molecule because it's trigonal planar and the peripheral atoms are the same. But if one of those peripheral atoms is different than the other two, or if 2 of them are different from the one, it is no longer symmetrical. This is no longer a symmetrical molecule. Trigonal planar molecules will also be symmetrical as long as all of the peripheral atoms are the same. But if that trigonal planar molecule, which isn't going to be trigonal planar in a moment, has 2 bonding pairs and a lone pair, and it's bent, it will never be symmetrical. Bent molecules are never symmetrical, even if the peripheral atoms are the same, because the bottom half of this molecule is different than the top. There are not multiple canceling planes of symmetry. Bent molecules are never symmetrical, even if their peripheral atoms are the same. And it's even more asymmetrical if the peripheral atoms are different. So again, bent molecules will never be symmetrical. Go to a tetrahedron. Tetrahedrons are also symmetrical. There are multiple planes that create symmetry that all cancel each other out. tetrahedrons are symmetrical as long as all the peripheral atoms are the same. But once we introduce a peripheral atom that is not the same as the others, the symmetry of a tetrahedron goes away. And if two of these were different from each other and the other two, it would further account for its asymmetry. So again, tetrahedrons will be symmetrical as long as all the peripheral atoms are the same. And if a tetrahedron has one or more peripheral atoms that are different than the others, it's not symmetrical. But if a tetrahedron has one of its electron groups being a lone pair, and then it's not a tetrahedron anymore, it's a trigonal pyramidal molecule, then it's not symmetrical. Trigonal pyramidal molecules are never symmetrical. The top half of this molecule is different than the bottom half. And if I swapped out one of these green atoms for a different atom, it would be even more asymmetrical. Again, trigonal pyramidal molecules are never symmetrical. And if I were to turn this tetrahedron into a bent molecule, because two of the four electron groups are now lone pairs, it will also be asymmetrical, because once again, bent molecules are never symmetrical. So the three molecular shapes that will always be symmetrical as long as the outside atoms are the same are linear molecules, trigonal planar molecules, and tetrahedrons. The molecular shapes that will never be symmetrical, regardless of the peripheral atoms, are bent molecules or trigonal pyramidal molecules. And here's a chart summarizing what you just heard. Linear, again, will be symmetrical if the peripheral atoms are the same. That is true of trigonal planar and tetrahedral, whereas bent and trigonal pyramidal molecules will never be symmetrical. Again, why that matters is we're about to learn what it takes to determine if a molecule is polar. If a molecule is polar. And a molecule will be polar if its bonds are polar and it's asymmetrical. On the other hand, a molecule will not be polar if either it doesn't have polar bonds, or if it does have polar bonds and it's symmetrical. Again, for a molecule to be polar, it has to have polar bonds and be asymmetrical. So the next step is to determine how we will know if in a molecule the bonds are polar. Because again, if the bonds in a molecule are polar and it's asymmetrical, the molecule will be overall polar. Well, that comes down to looking at the difference in electronegativity values between the two atoms that are sharing electrons in the molecule. If it's nitrogen and oxygen that are sharing electrons, oxygen's electronegativity value is 3.5, nitrogen's is 3.0. The difference between those is 0.5. The cutoff for a bond to be polar is technically 0.3. If the difference in an electronegativity between two atoms that are sharing electrons is 0.3 or greater, we say that that bond is polar. But the reality is most nonmetals that share electrons will have a difference in electronegativity of greater than 0.3. So you can always refer to your periodic table to find what the difference is, but it's also okay to assume that if the atoms are different, it's likely their electronegativity difference is greater than 0.3 and the bond will be polar. But if two atoms are the same as each other, if two oxygen atoms, for example, are sharing electrons, their electronegativities will be the same, their difference will be 0, and absolutely will that bond be nonpolar. So again, two atoms, if their electronegativity difference is 0.3 or greater, will have a polar bond, or for the sake of simplicity, you can assume that if the atoms are different, the likelihood is their difference in electronegativity is greater than 0.3 and the bond will be polar. So what is a polar bond? What does that mean for a bond to be polar? Well, as we can see here in this diagram, in the middle diagram, where it says polar covalent bond, it is telling us that bonds that are polar are from electrons that are shared unequally between the two atoms. The idea is that if one atom has a higher electronegativity than the other, it has a stronger attractive force for those shared electrons. Those shared electrons will spend more time with, be closer on average to the element with the higher electronegativity value. And what that does, because now there's more negative charge being spent on one atom than the other, is gives the atom with the higher electronegativity a slight partial charge. This delta negative means partially charged, partially negatively charged. On the other hand, the atom with the higher electronegativity value will be spending less time with these electrons and will have a partial positive charge, denoted delta positive. A nonpolar bond, on the other hand, that would exist absolutely between two like atoms, chlorine, are equally shared. The electrons are equally shared. They spend the same time with each atom, and neither atom ends up being partially charged. Both atoms end up being overall neutral. And we see, of course, to the right, an ionic bond where the difference is so great, greater than 1.7, the electrons aren't shared at all. They're transferred, and each atom ends up with a full charge, as opposed to being partially charged. If we take a look at another model, we see a water molecule, which, by the way, is polar because its bonds are polar, and it's asymmetrical. It's bent, depicted here. And see these dots? They're spending more time with oxygen than hydrogen. Oxygen's more electronegative than is hydrogen. The negative charge, spending more time with oxygen, renders oxygen partially negative and hydrogen partially positive. So this is a polar bond in an asymmetrical molecule, rendering water polar. All right, we flipped the page. We're now on 380 of our textbook, looking at this diagram at the top, figure 666. Well, what is a polar molecule? What does that mean? And why, in this case, is water polar? Maybe we know already, and carbon dioxide nonpolar. A polar molecule, once again, will be polar when the bonds are polar and it's asymmetrical. Water we know to be polar. Oxygen is more electronegative than hydrogen. Oxygen ends up being slightly positive, and the hydrogens end up, oxygen ends up slightly negative, the hydrogens end up slightly positive. What that means, since the hydrogens are on one side of the molecule and oxygen on the other, it's not symmetrical, is that the hydrogen end of the water molecule will be slightly positive. The left side of this water molecule, the way it's oriented, is slightly positive, and the right side is slightly negative. This arrow that is drawn from the hydrogen side of water to the oxygen side of water is called a molecular dipole, or a dipole moment. And those are drawn to indicate which side of the molecule is more negative. It goes from the positive side to the negative side. And in this case, it's going from hydrogen's side to oxygen's side. What that means is there is one side of the molecule that has a different charge than the other side. The oxygen side is slightly negative, the hydrogen side is slightly positive. When a molecule has differently charged ends or sides, like water does, it's polar. And what that means is that there's an opportunity for the negative side of a water molecule to be attracted to the positive side of another water molecule, or to the positive side of another polar molecule. Carbon dioxide, though, is nonpolar. The reason why it's nonpolar isn't because its bonds aren't polar. Carbon dioxide bonds are polar. The oxygen is quite a bit more electronegative than the carbon, but it's a symmetrical molecule. So what that means is that in both cases, oxygen is pulling electrons away slightly from carbon. Both oxygens will be slightly negative. But because it's a symmetrical molecule, both of the outer ends are negative. Neither outer end of carbon dioxide has a different charge than the other. They're both slightly negative. There's therefore no opportunity for the positive side of one carbon dioxide to be attracted to the negative side of another. Both outer edges are negative. Carbon dioxide, again, is nonpolar because although its bonds are polar, it's symmetrical. And what that means is those polar bonds cancel each other out. The bond dipoles cancel each other out, rendering the molecule overall nonpolar. If we look down at figure 667, we see two tetrahedrons side by side, one that's nonpolar and one that's polar. In both cases, the bonds within these two tetrahedrons are polar. Chlorine is quite a bit more electronegative than carbon, which is why we see the arrow pointing from the carbon to the chlorines. What that means is all the chlorines on the outside will be slightly negative. All the chlorines on the outside will be slightly negative. But if all of the outer edges of the molecule have the same charge, if they're all slightly negative, the molecule is not polar. So this is a nonpolar molecule because although the bonds are polar, it's symmetrical. And those polar bonds cancel each other out, rendering the molecule once again nonpolar. But in the molecule to the right, CH3Cl, which is a tetrahedron, The bonds are polar. The carbon-hydrogen bond is polar. Carbon's more electronegative than hydrogen. The carbon-chlorine bond is polar. But it's not a symmetrical molecule. It's not. The bottom part of the molecule is different than the top. And what you can see here is all the electrons are getting sucked up toward the chlorine end. And in this case, the chlorine will be slightly negative. The top part of it will be slightly negative, and the bottom part would be slightly positive. And because one side of the molecule has a different charge than the other, it is polar. So here's a case where this molecule is polar because the bonds are polar and it's not symmetrical, meaning the bond dipoles don't cancel each other out. And down here in pink, this is the question we always ask ourselves, which you've heard me repeat multiple times. Does the molecule contain polar bonds? It needs to be polar. And if so, do the bond dipoles cancel each other out or not? If they do cancel each other out, it's not polar, meaning if it's symmetrical, it's not polar. But if they don't cancel each other out, if it's asymmetrical, it will be polar. And I flipped my page. I'm on page 381, and stated here is what you just heard me say. So if you want to pause and take a peek at this and make sure it agrees with what you just heard, you might consider doing so. All right, so we're going to do 3 quick practice problems together, and then that will be the end of this lecture. Here is NH3 ammonia. Here is its molecular formula. I encourage you to draw the Lewis structure, to figure out what the shape is, use your understanding of Vesper to figure out its shape, then to ask yourself, does it contain polar bonds? And is it symmetrical or not? Is this molecule polar? So consider doing that, pausing the video, and coming back to see my solution here in a moment. So there's ammonia's Lewis structure, nitrogen, single bonded to 3 hydrogens with a lone pair at the top. Hopefully you know that when there's 4 electron groups, 3 of them are bonding, 1 is a lone pair, it forms a tetrahedron, but I say that in quote marks because when one of those electron groups is a lone pair, it in fact is not a tetrahedron, it's a trigonal pyramidal molecule. So these are polar bonds. N is more electronegative than hydrogen by more than 0.3, and will suck the electrons away from hydrogen. NH3 is not a symmetrical molecule, so this is an overall polar molecule where the top end of it, the nitrogen end, will be slightly negative, and the hydrogen end will be slightly positive. That blue arrow I've drawn to the right of the Lewis structure is the dipole moment, or the molecular dipole, indicating that, again, the bottom is slightly positive and the top is slightly negative. Here's the carbonate ion, same thing. Consider drawing its Lewis structure, predicting its overall geometry, and then deciding if it's polar or not. Come on back when you've done that. So there are carbonate's Lewis structures because carbonate, as we learned earlier, exhibits resonance. That double bond is not localized between the carbon and 1 oxygen, but rather is delocalized, and those extra electrons are shared evenly amongst the carbon and all the oxygens. So one way to depict that is to show the 3 possible Lewis structures, but again, none of these are accurate. It's not like a third of the carbonates are one way, a third are the other way, and a third are the third way. Rather, those electrons are distributed everywhere, and a way we can indicate that is by using the old dotted line to say, well, those electrons are everywhere. That's pretty poorly drawn. So as far as the polarity of this molecule goes, because the bond is polar, but the molecule is symmetrical, this is not a polar molecule. The oxygens on the outside are more electronegative than the carbon in the middle. The oxygens will all be slightly negative, but again, because it's symmetrical, all the outsides will be slightly negative. There'll be no difference in the overall charge on the outside, and this is a nonpolar molecule. All right, one more. Here is H2S, hydrogen sulfide gas. Draw the Lewis structure, figure out what the geometry will be. Ask yourself, does it have polar bonds? And is it asymmetrical? And if so, is it polar? So there's the Lewis structure. We've got 2 bonding groups to each of the 2 hydrogens, 2 lone pairs. There are 4 electron groups, 2 bonding groups, 2 lone pairs. They will spread out evenly in space to make a tetrahedron. But remember that when there are 2 lone pairs and 2 bonding pairs, it isn't actually a tetrahedron. It is bent or V-shaped, because all we're contemplating is what it looks like with just the atoms in mind. So this is a bent or a V-shaped molecule. S is quite a bit more electronegative than sulfur, so those bonds are polar, but because the molecule is asymmetrical, the molecule will also be polar. Because these bond dipoles don't cancel each other out, the molecule will be symmetrical. There's my bond dipoles, and here's my dipole moment, or my molecular dipole, indicating that the top half, at least the way I drew it, the sulfur end is slightly negative and the hydrogen end is slightly positive. So hopefully that allows you to predict if molecules are polar or not. Thanks for hanging in there with me. Congratulations for watching the last winter break lecture, and I'll see you soon.